Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cusp River College in Sacramento, California. I couldn't really create a really interesting or informative name for this video because what we're going to be talking about here is how to determine whether a function is actually differentiable at a or on an interval a. So differentiability, to be or not to be, that is the question. That's what we're dealing with. You are assumed to already know the true definition, the limit definition of a derivative. You should be able to work with that. And you should be able to also scroll out the graph of a derivative given the graph of a function. So we covered that so far. And so let's go ahead and talk about the existence of derivatives and when they don't exist as well. So first with the definition, right? Well, our function is said to be differentiable at a if f prime of a exists. Okay, and remember f prime of a is a limit, right? We know that from previous material. F prime of a is just a limit. It's equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. And if you're watching this video series in order, then you might be wondering why I rarely use this one, but it is the same. So you could go ahead and say, or f of the limit as x approaches a of f of x minus f of a over x minus a. You can use either of those. I just happen to use the first one just because that one works just as much as the other. Okay, so we know it's differentiable at a if f prime of a exists. So if that limit exists, it's said to be differentiable on an entire interval if it's differentiable for every number on the interval. In other words, if I give you an interval I, for f prime to exist on I, for f prime to exist on I didn't actually give myself room there. F prime of x must exist for all x in the interval I. So you would theoretically have to test every number in the interval, but that's not actually true. There are a lot of tricks that we can take advantage of from our previous work with limits to showcase that our limit exists on that entire interval. Remember that early on in this course when we were dealing with limits, and that's what a derivative is a limit, that we had said, you know what, a limit exists for most of the functions we deal with as long as there's not a domain issue. That was a direct substitution property. So as long as there's not a domain issue, the limits will exist. So that's how you can really avoid testing every point in a domain. Now there are actually 3 ways to tell that a function's not differentiable at a point if you're given the graph of a function. So this is all dependent upon somebody giving you the graph of a function. So the first way you can tell that a function given the graph is not differentiable at a point is if that function has a cusp or a corner at that point. So what do I mean by a cusp or a corner at that point? Well, let's suppose that you have a graph. It's pretty smooth, and all of a sudden does something like that, and then that. These are called corners because by definition, and this is, by the way, hard to find a good definition for a corner, but essentially what it means is that the slopes of the tangent lines from one side are finite, but don't match the slopes of the tangent lines from the other side. So I'll write that down actually. So a corner occurs at x equals a if the limit from the left And these limits, remember, are derivatives. So the derivative from the left is not equal to the derivative from the right. Yet both of these derivatives are finite. That's how a corner is pretty much defined. It's hard to find that definition, by the way. But you could see, like, for example, here, the derivative from the left looks to be, let's say, a positive 2. And the derivative from the right looks to be a negative 2. So they don't match up. The slopes from the left and right don't match up. So therefore, this is called a corner. Also, that means the derivative doesn't exist because your left and right hand limits don't match. That means the limit itself doesn't exist, right? If the limits don't match, there we go, I just wrote it down. If the single-sided limits don't match, then the overall limit just doesn't exist. That's why the derivative doesn't exist at that point, whatever that point is. And by the way, the same thing over here, right? That is a corner as well. The derivative from the right is not the same as the derivative from the left. That is, the slopes of the tangent lines from the right are not the same as the slopes of the tangent lines from the left. So therefore, that is a corner. Now, cusps are slightly different. And your instructor, if they're anything like me, they're probably not going to pick on these definitions. I don't actually whip out a definition like this during an exam and say, state this is a cusp or a corner, and if you're wrong, you lose all your points. It's the fact is, I do ask, I'll hand you a graph and say, is this differentiable or not? Why? Okay. But a cusp just has a completely different behavior. It kind of does this. So, well, I guess I didn't need a y-axis in there. Looks something like this. You have something that seems to be going to infinity and then coming back down. So when I say seems to be going to infinity, I mean the slopes of the tangent line seem to be going to infinity. And so this would be called a cusp. Very finely differenced detail between those two. And a cusp basically occurs at x equals a if one of the limits that are derivative limits tends to infinity. So you can see by my statement there that either the left or the right hand or both limits tend to infinity. Then you have a cusp. There is a slight modification to both of these that I need to mention here. F of a, our function would be still continuous. So this, how do I want to state that? There, that's how I'll state it. In both of these cases, we are only dealing with functions that are continuous at these points. So let me hop back. The graph has a cusp or a corner at a point. And not only does it have a cusp or a corner, well, the fact that it has a cusp or a corner at the point means that it's continuous. It's totally continuous at that point. It's just that the slopes of the tangent lines don't match up from left and right. So this function, you notice, is continuous, but the slopes from the left and right don't match up. So that would be called a corner. The function down here definitely is continuous, but the slopes from the left and the right don't match up. And in fact, from the left-hand side, it looks like the slopes are going to infinity. So that would be called a cusp. They're very finely detailed points that not a lot of people are going to hold you to, so don't worry too much about that. The second reason why, or a second way we could tell that the graph of a function is not differentiable at a point is if it's not continuous at that point. That's why I mentioned that these are continuous, because I'm saving the not continuous part for the next one. So if you have a function that's not continuous, let me go ahead and just put a bar here. If we have a function that's not continuous at a point, say it does something like this, and there's an open hole and it picks up right here, then it's not differentiable at a. So f prime at a does not exist. And this actually bothered me for a long time when I was a student, because I had a really hard time with the idea that the derivative wouldn't exist if there was some type of, jump discontinuity or whatever. In one specific case, I thought, well, what if you have a horizontal line all the way up to, let's just say, -3, and then it hops up just by 1 unit, and it's still a horizontal line, right? So let's say this height is 1 and this height is 2. Well, you can see from the left and the right, the slopes are the same. They're both 0. So why doesn't the derivative exist at -3? And it wasn't until I actually spent time with derivatives in Calc 2 that I finally figured it out. But it's because of the definition of a derivative. The derivative says the following: the limit as h goes to 0 of f of -3 plus h minus f of -3 all over h. Well, okay, let's see. We're going to have to break this into two cases. So let's take a look at the left-hand limit, the limit as h approaches 0, but from the left-hand side, of f of -3 plus h minus f of -3, and that's all over h. Well, again, I'm allowing h, the wiggle away from -3, I'm allowing that to be negative. So my h might have drawn me back here. This is -3 minus h right here. And the height, the function height at f of -3 plus h is negative, so I'm going to say plus h. The height is going to be a height of 1. All right, so I'll just plug that in. That's going to be limit as h approaches 0 from the left of 1 minus, and then f of -3, well, that's also 1. Okay, that's perfect. All over h. 1 minus 1 is 0. Now, this is a good example that I accidentally made up. Algebra, arithmetic before algebra, algebra before trig, trig before pre-cal, pre-cal before calculus. And I'll tell you one thing I know from algebra or arithmetic: 0 over anything is 0. Now, some people will argue and they'll say, wait, no, that's 0 over 0. No, it's not. It's 0 over something approaching 0. It's a concrete 0, a set in stone 0 over something not necessarily 0. So a set in stone 0 over any non-zero number is going to be 0. So great. I find that the slope, when I look to the left, is 0. Yay! And that's exactly what we know. We know the slopes of these lines are 0. So you say, well, then what's the problem? Well, let's take a look at the limit as h approaches 0 from the right. Well, we have f of -3 plus h minus f of -3 all over h. But now h is allowed to be positive. So instead of wiggling to the left, h is wiggling to the right. So this is -3 plus h. And that point right there is f of -3 plus h. So let's see what this is. It's the limit as h, limit as h approaches 0 from the right. F of -3 plus h is 2 in this case. Minus f of -3 is 1 all over h. And notice in this case, that is not 0 over h. It is 1 over h. Limit as h approaches 0 of 1 over h. And that will be infinity. Notice the left and right hand values do not match. So therefore this limit does not exist, and therefore the derivative doesn't exist. The issue here is that you're essentially saying, I'm connecting this dot to this dot, and then I'm going to drag that dot that's to the right closer and closer and closer. You can see those slopes get closer to infinity. So that's why, because the left and right hand limits just don't match. Even though the slopes are the same on the left and the right, the left and right hand limits just don't match. Okay, so that's a second reason why you can tell from a graph that a derivative will not exist at a point. It's just not continuous. And the final one is that the graph has a vertical tangent line at a point. If you have a graph that has a vertical tangent line at a point, then you totally know it's not going to have a derivative there. Now, I want to be very clear about this. Having a vertical tangent line does not mean you have a vertical asymptote. It can mean that, but it doesn't necessarily mean that. So for example, you could have at x equals a vertical asymptote. That's perfectly fine. It's supposed to be red. You could totally have a vertical asymptote there. In that case, I know the derivative doesn't exist because the function doesn't even exist there. There's a discontinuity. Okay, so once we have a discontinuity, we know the derivative won't exist. So that's actually part of the earlier justification. We need our function to be continuous. However, what if we do have a continuous function without a vertical asymptote? And I'll show you one right now. We've actually graphed it in this course before. This is y equals the cubed root of x. It actually goes vertical at x equals 0. It briefly goes vertical at x equals 0. So the tangent lines go vertical at x equals 0. And you say, well, okay, why does that say that the derivative doesn't exist at x equals 0? Well, let's go ahead and use the definition of a derivative. If I say y prime at 0 is equal to, okay, well, that should be the same thing as, actually, you know what I'm going to do is I'm going to find y prime at x, not just at 0. So let's go ahead and do that. Y prime at x is equal to the limit as h goes to 0 of the cubed root of x plus h minus the cubed root of x all over h. Now this actually, when I made this up, I didn't mean for it to be so tough, but it is going to be a tough one that I'm doing here. It might have been much easier to do this at 0 itself. So I can do this, it's just a difference of cubes, but I don't want to spend all day actually coaching you through that. So instead, let's go ahead and just say y prime at 0. If we have time at the end, maybe I'll show you the general one. But y prime at 0 is much easier to deal with here. So let's see, we have the cube root of h minus 0 all over h. Limit as h approaches 0 of the cubed root, h to 1/3, over h. And that will be the limit as h approaches 0 of 1 over h to the 2/3 power. And you can see right now that does not become finite. In fact, that blows up to infinity. And as such, this limit not being finite means that the derivative does not exist. So I harp on it early in the course that infinite limits do exist, but when it comes to derivatives, you need finite values as their output. So in this case, we would say the derivative is infinite, so therefore its value does not exist. I know that can be a bit obscure for people, but it is true. Normally with limits, if I can find that a limit is infinite, if I can say, oh yeah, that limit's totally infinite, from the left or from the right, it doesn't really matter. They match up, they both become infinity. Then we would describe it as being infinite. But when it comes to talking about derivatives themselves, we want those derivatives to exist and be finite. Because you don't want to say, oh, the derivative of that function is infinity. That doesn't make sense. You want derivatives to be finite numbers. So let's take concrete examples of what we've been talking about. Let f of x equal the absolute value of x squared minus 4. As you know from your pre-calculus course, it's just x squared minus 4, right? A parabola shifted down 1, 2, 3, 4 units, something like that. But then you take its absolute value. Go ahead and get this ready for my graphing. You take its absolute value and it will flip or reflect those negative y values up above. So that is actually the graph of f of x. And you can see, by the way, we have at -2 and 2 corners. So we know just from the last statement that the derivatives should not exist at -2 and 2. Now, I didn't even bother reading the problem, but I probably should have. It said sketch f, which we just did by accident, and use this to sketch f prime. So let's go ahead and sketch f prime. Again, I'm going to mark out derivatives. The derivative is 0 there, so I'm going to plot 0. The derivative, let's say here, is a negative, I don't know, let's say that's a negative 4 actually. Okay. And maybe the derivative, actually, let's say the derivative there is negative 2, just for plotting purposes. And derivative right about here is a negative 4. And the derivative right about here is a positive 2, and derivative right about there is a positive 4. So I'll put red dots actually where my derivatives are being plotted. So those red dots represent the slopes of the tangent lines at those points. But notice that actually the derivative at 2 itself doesn't exist because the limits from the left and the right are different. So what I'm going to do is I'm going to create a little open hole here and another open hole right about here. Hopefully that matches up. Sort of does, sort of doesn't. Okay. And then now let's consider the derivatives, let's say right here. Well, that's very steep. That's probably a derivative of, I don't know. Let's say something higher than 4, let's say 6, and that is steeper, so that might be 8 or something like that. So I'm going to go ahead and say 6 and 8. I'll just do that, 6 and then 8. Something like that. And likewise, in the other direction, this would be like a negative 6 and a negative 8. So I'll plot negative 6 and negative 8. Something like this and this. Okay. Let me zoom out so you can see this. Connecting the dots. It's a nice, pretty smooth line. This kind of matches up with our investigation of graphs earlier, that if you have a second degree polynomial, its derivative looks to be a line. And then looks like it picks up after that and continues to be linear just in the other direction. So it looks something like this. That's an interesting graph. You could see, by the way, the derivative's totally, the derivative function is not continuous, right? Doesn't exist at 2. State where f is not differentiable. Well, we can easily see 2 and negative 2, plus or minus 2. Now prove that it's not differentiable at these points. Well, that's okay. I can totally do that. So that in general, the derivative is defined to be that limit of h goes to 0 of the difference quotient. Now, because we are dealing with a polynomial, or maybe I should go the other direction. Maybe I just say, let's start by proving that the derivative doesn't exist at plus or minus 2. So let's worry about plus or minus 2 here. You can, by the way, insert the function in here. Limit as h goes to 0. The function, again, is the absolute value of the quantity x plus h being squared minus 4, and absolute value, and then minus the absolute value of x squared minus 4. Okay. All over h. That's just the general form. So if x is between negative 2 and 2, then the argument, let me highlight our argument right here. That argument is going to be negative. You can try it out. Plug in 1 or 0, whatever you want. Any number between negative 2 and 2, you'll find out that argument is negative. And that will imply that the absolute value of that argument can be replaced with the opposite of x squared minus 4. Also, since h is going to 0, it's going to be a very small distance away from whatever point we're looking at. So we can assume that it's close enough to 0 so that x plus h squared minus 4 is still negative. Okay, I'm just basically saying that if you're only looking at, let me showcase this here, a little bit of a mess. If you're only looking at the x squared minus 4 function, let's just look at that, negative 2 and 2. I can pick any x value between negative 2 and 2, and you could agree that x squared minus 4 is negative. There's no arguing that, okay? But let's suppose I pick a concrete x value. I'm like, you know what? The one I want to pick is this guy right here. And then I say, but I'm not going to look at that x value. I'm going to look at x plus a small wiggle. Well, I can make that wiggle as small as I want, right? Because that wiggle is h. This is x plus h right there. I can make that wiggle as small as I want. And so therefore, I can get it close enough to the x value that's between -2 and 2, so that still its y value will be negative. That's all I'm saying. Even if you try to park x right next to 2, h will be small enough so that x plus h will still be to the left side of 2. We're okay. And therefore, I can tell you that x plus h quantity squared minus 4 is also negative, and that would imply that the absolute value of that, x plus h squared minus 4, is going to be replaced with the opposite of the quantity x plus h and quantity squared minus 4. Okay? Not too bad. So then I'm kind of proving the whole thing. So on -2 to 2, you have the following. F prime of x is equal to the limit as h approaches 0 of, instead of the absolute value of x plus h squared minus 4, I'm going to write it as the opposite of the quantity x plus h squared minus 4 minus, again, the opposite of x squared minus 4, and this is all over h. Now we have some distributions, nothing huge. Limit as h goes to 0. This will be the opposite of, I'm going to multiply out that stuff and apply the opposite. That'll be opposite of x squared. It's the opposite of 2hx, the opposite of h squared, and then plus 4. And this will be plus x squared and minus, so minus 4 all over h. And collect like terms, the 4's cancel beautifully, the x squareds cancel beautifully. A power of h will disappear out of each term in a numerator, and you'll have, I should actually write that. Limit as h goes to 0. We'll have h times -2x minus h all over h, and you see the h's will cancel, and we can do direct substitution. Allow h to go to 0, and you get -2x. Okay, that's not too terrible. A similar argument can be used for x being strictly greater than 2 and x being strictly less than -2. So I'm not going to worry about those two arguments. Instead, I'm going to focus now, finally, on x equals 2 and x equals -2 themselves. And I'll start with, and only do, honestly, x equals 2. So f prime at 2. We're going to concentrate on that. Well, I need the derivatives to be the same on both sides of 2. So I have to look at the limit as x approaches 2 from the left, and then I'll look at the limit as x approaches 2 from the right. And this one, notice the definition of the derivative that I'm going to be using here. Instead of a, we're using 2, and I'm using this definition just because I think it's a little bit easier in this problem. Now, as x gets really close to 2, but from the left, what does our function look like? Well, limit as x gets really close to 2 from the left, our function is, remember, the absolute value of x squared, x squared minus 4. Let me just double check that. Minus f evaluated at 2, which is 0, all over x minus 2. So far, so good. However, you're approaching 2 from the left. So you have numbers smaller than 2 that you're plugging into this. And so therefore, this picture inside here is actually negative. And remember what happens with absolute values. The true definition of an absolute value tells us that if you have the absolute value of something and that something was supposed to be negative, the absolute value will return the opposite of it. It's critical to note. And now I can factor that x squared minus 4. So I have opposite of x minus 2 and an x plus 2 all over x minus 2. The x minus 2's cancel beautifully, and now I can do direct substitution. So direct substitution gives me the following, negative, and then I'm inserting a 2, so negative 4. So the derivative from the left looks to be a negative 4. The slopes of the tangent lines from the left look to be a negative 4. And if you look at our graph here, from the left-hand side of 2, yep, those slopes are totally negative, and they're approaching a slope of negative 4. Now let's look at the right-hand side of negative 2. Let's see how much paper I have. Yeah, I have plenty. So let's look at the right-hand side of negative 2, or positive 2, sorry. So x approaches 2, but from the right-hand side of f of x minus f of 2 all over x minus 2. Let's see. F of x, again, is the absolute value of x squared minus 4. F of 2 is 0. X minus 2. Now, because x is approaching a number greater than 2, right? X is approaching 2, sorry, but it's from the right-hand side, so it's x is slightly greater than 2, so x squared is slightly greater than 4, so this number right here is positive. Well, then I don't need the absolute value signs. If you already have a positive number, you can erase those absolute value signs. That numerator will factor fairly easily to x minus 2, x plus 2 over x minus 2. And the x minus 2's cancel. And you can do direct substitution. And we get a value of 4. Notice that's not the same as the left-hand limit. The left and the right-hand limits do not match. So since the left and the right-hand limits do not match, the limit just does not exist. And that implies that f prime of 2, because that's what the limit was f prime of 2, does not exist. Remember, derivatives are just limits. You need both left and right-hand limits to exist and match. I think I'd stop that one there just because you can do the rest. If you want to showcase it doesn't exist, the derivative doesn't exist at negative 2, you go through all the same steps that I just went through, but you're doing it at negative 2. If you want to showcase the function is differentiable for numbers greater than 2 or less than negative 2, you do the same thing I did initially, which is just grab a number greater than 2, for example, and then go through that similar argument. No need for me to go through the rest of it, though. And finally, in this video, we get to probably the most important theorem in this section. If your function's differentiable at a point, it's continuous at that point. I will often state it slightly differently. Differentiability implies continuity. Differentiability is a long word, by the way. So, very, very important. If you have a differentiable function, you know it's continuous. If you know your function's differentiable from 1 to 10, you know it's continuous from 1 to 10. The converse of this theorem is totally not true. Just because you have a continuous function does not mean it's differentiable. And just look at the last example. This function right up here. That's a continuous function. It's continuous on this entire interval here, but it's definitely not differentiable at negative 2 and 2. So continuity does not imply differentiability, but differentiability implies continuity. All right, that being said, let's go ahead and take the time to prove this. This is something that a lot of people don't want to do, but we're going to prove this. So let's talk about how to prove something like this. It's somewhat of a straightforward proof, but there is a little bit of a setup so that we get to know how the proof is designed. So this is an if-then statement. If f is differentiable, then it's continuous. So you get to assume the if part. And then you look at that and you say, well, what does that mean? Right? What the heck does it mean that f is differentiable at a? Just start reaching into your bag of definitions and say, well, then this means that f prime at a exists. It's equal to the limit, as there's two different versions. I'll write them both down just in case I need them. The limit as h approaches 0 of f of a plus h minus f of a over h. It's the same as the limit as x approaches a of f of x minus f of a over x minus a exists and is finite. Okay, so that's what we have to go with. We have this definition. F is differentiable at that point A, which means either those two limits are true, they exist, and they're both finite. Now what I'm going to do, because I know that to prove something's continuous, you want to prove that the limit as x approaches a of f of x equals f of a. Because of that, specifically the limit as x approaches a, I know that I'm going to want to keep this one. This is the one I'm going to want to work with. I don't really want to work with the h approaching 0 because it just doesn't work out. And the way I'm going to write this proof might start a little weird for you. That's because I've done a lot of work in the background to make sure it works out. But this is how I'm going to do this. So suppose that we have f is differentiable at x equals a. Well, what does that mean? It means f prime of a exists, and it equals the limit as x approaches a of f of x minus f of a over x minus a. Now, consider the following. Now, these are little pieces of a proof. When you say consider, you're allowing somebody to look at something that might seem like an aside. The limit as x approaches a, so notice I'm sneaking in that limit as x approaches a there, of f of x minus f of a. Well, that you would say, oh, that's 0 because x is approaching a. But we don't know that that's 0 because we haven't proven that this function's continuous at a. We just don't know that that's 0. So you can't just plug in a. All right? We do not know that f is continuous at a. So you cannot do direct substitution here. But what you can do is you do a little algebraic manipulation, something that is often done in mathematics, where you kind of either add and subtract something or multiply and divide by something. And in this case, I'm going to multiply and divide by the same number. So f of x minus f of a. And I'm going to multiply that numerator and its corresponding denominator by the following. X minus a over x minus a. So really, I'm not doing anything spectacular here. I'm just saying multiply by the number 1. Most people will nod their heads and say, okay, well, that seems perfectly fair that you're doing it. I'll accept that. And I say, great. If you accept that, I'm going to go ahead and just use a property of arithmetic and rewrite that fraction as f of x minus f of a over x minus a times the quantity x minus a. Most people would still nod their heads. Okay, I'm with you. And you say, well, okay, but don't we both exist, or don't we both agree? We do both exist, but don't we both agree that earlier we stated the derivative at a existed? That was the beginning of this proof. Suppose that f is differentiable at a. They nod their heads and they say yes. And then you say, so therefore you're okay with me breaking this into two different limits. One being the f of x minus f of a over x minus a as x approaches a, and the other one being the limit as x approaches a of x minus a. And they nod their heads and I say, yeah, of course, because the first factor here, this guy right here, we know that exists because we said the derivative exists. And the second factor, well, that's just an identity. That's a limit law. As x approaches a, that we could totally do that. That will just be 0. And you say, oh, I'm sorry, you said it would be what? And they say it would be 0. And you say, oh, okay. So you're okay with me saying that this picture's f prime of a. And they say, of course, we've assumed that. And you just told me as x approaches a, the limit as the limit as x approaches a of x minus a, you told me that was going to be 0. They say, yeah. And you say, great. I just want to make sure we're on the same page. So that's equal to 0. They nod their heads. You say, great. And then they say, but where are you going with this? You say, well, hold on. However, the limit as x gets really close to a of f of x, and then your crowd leans forward. They know, like, okay, you want to prove that this is equal to f of a to show continuity. You're like, yes, I am going to show continuity by proving that this is equal to f of a. This is equal to, if you would please agree, the limit as x approaches a of f of a. And they say, no, it's not. And I say, you're right, it's not. It's equal to the limit as x approaches a of f of a plus f of x minus f of a. So really, I've just written the same picture. The limit as x approaches a of only f of x. That f of a is being canceled by the negative f of a. So those are kind of offsetting each other. So I really haven't done anything. Okay, they nod their heads. Sure. And you say, great. But this is equal to, whoops. But this is equal to the limit as x approaches a of f of a plus the limit as x approaches a of f of x minus f of a. And they say, yeah, if that limit as x approaches a of f of x minus f of a existed, sure, I totally would agree with that. And you say, well, you do totally agree with that because that's this picture right here. And we've just shown that that limit is 0. And they kind of stand there in stunned silence as you say, okay, so since I've already shown you that this limit is 0, this is just going to be the limit as x approaches a of f of a. But isn't f of a finite number? And they nod their head dumbly, and you say, so therefore that's just f of a. Thus, the limit as x approaches a of f of x must be f of a, which implies f is continuous at x equals a. QED. So that's, it's a pretty beefy theorem, or a proof, but a fun proof to do. It really includes a lot of the information that we had. Now, you might be wondering, like, how the heck would I have even started with this idea that I'm going to take f of x minus f of a? Well, how I did is I did a bunch of scratch work until I figured it out. Once I figured it out, it was like, oh, yeah, okay. So I know that I want to abuse this form right here because we were assuming that was existent and finite. So once I knew I wanted to work with that form, I decided, okay, let me just work with its numerator first, and then I'll attach to that by multiplying by 1 in the form of x minus a over x minus a. I'll attach to that the x minus a. And then once I got that, it was almost all easy from there because you get this, you could break it. The right break turns to 0. The left break we said was finite. And so that ends up being 0, that difference between the function and f of a. And then I started with my actual proof, which is that the limit as x approaches a of f of x, I want that to be f at a. And I just manipulated using arithmetic. It's a really, really cool way of doing a proof. It's a direct proof. It takes a lot of experience and a lot of time to kind of be able to pull together a proof like that. But once you can, it is pretty liberating. It's kind of neat. Anyhow, I think that's way more than enough for this video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close. Don't talk too much that isn't kosher. inside that doesn't justify you to speak too loud and cry.